All right, welcome everyone. So today we are having a little mini lecture on the satisfiability problem, SAT. It is a fundamental problem in algorithms, specifically within the NP completeness field, and coincidentally, it is also the very first, the original NP complete problem. Okay, so let's dive in. So what is a satisfiability problem? It's essentially that we're given a Boolean formula. We just have to identify whether it has a satisfying assignment or not. So let's suppose the formula is given as x1 or x2 or x3 and x1 or not x2 or not x3. So in these terms, we're given a long formula. It has these conjunctive clauses, which are highlighted by this and, which are each of them are set of disjunctions inside. So that means any of this could be true. This clause would be true. And then we have to find something that's true here. So that's essentially what we have to do here. All we have to do is we have to say, okay, let's suppose x1 is true, x2 is false, x3 is true, x4 is false, etc., etc. So we could have a formula with hundreds of literals inside it, and we have to give it a satisfying assignment. That's what we are asked to do. So that means we choose x1, x2, x3, x100 up till true or false, such that this entire formula becomes true. If we can find such an assignment, we say that this formula is satisfiable. And if we don't find it, then really we're not sure if we just didn't find it, or maybe the formula is not satisfiable entirely. And if we can somehow prove that the formula is not satisfiable, then we would say that the formula is not satisfiable at all. So that's in essence the satisfiability problem. The beauty of this problem is very easy to explain to anybody, and you can kind of even give that to younger students, to younger kids, saying, hey, go ahead and try to find it. They can try to find an assignment. If they find it, it's kind of like solving a little maze problem. Right? So here's a little SAT input. If when we consider programmatic inputs here, we can be given a text file. The text file just kind of looks like this. It's one clause per line, each literal replaced, separated with a comma. And that's all that is. There's just a text file here, 1, 17, 30, which translates to x1 or x17 or x30. And if we're given this prime symbol, the apostrophe, then we can say that's the not. So 2, 16, 18 prime, that means that x2 or x16 or not of x18. So not of x18 means that if x18 is true, then this not of x18 is false, and vice versa. So this file has a very simple structure. It could have 1,000 lines to it. Each line represents one clause, and each clause has some literals inside it, given just by the numbers. So very simple input, overall a very simple problem. Now, if somebody does give us a solution or a proposed solution to the satisfiability problem, we can verify it very easily. We can verify it very easily just by going through all the clauses, seeing, do all the clauses check out? Does each clause have at least one true literal inside it? And then if so, then we say, okay, yes, the given solution is correct. And if we find that the given solution has missed something, we can say that the given solution is not correct. But it's very simple linear time kind of verification algorithm. And we also are told that the SAT problem is an NP. And these two statements are not a coincidence. This is just the definition. When we say that a problem has a very simple polynomial time verification method, that problem is by definition in NP. Okay. Just the verification means that it is in NP. Before we study sort of the significance of SAT, let's see what are some of the variations of SAT. There are many different variations of this satisfiability problem. Many of them are commonly referred to as KSAT. So the version that we just saw earlier was a version that's called 3SAT. That means there are many clauses, but each clause has exactly 3 literals. So that is called the 3SAT. And that problem is NP complete, as we will also see a little later as well. And there is also a version called the 2SAT, which means that each clause has only 2 literals. And that version is actually solvable in polynomial time. There can also be some other versions, such as maxsat, which means that simply try to maximize the number of clauses that can be made to be true. There can be a counting sat, find all the truth assignments that make the clause to be satisfiable. And maxsat and counting sat are also hard problems. Counting sat is, in fact, considered even harder than maxsat. And maxsat is also NP complete. So those are some of the variations of the satisfiability problem. Let's try to solve the satisfiability problem. Just because the problem is NP complete, or in other words, it's a hard problem, does not mean that we should not try to solve it or it's not solvable. All it means is that we are not really super likely to find a polynomial time algorithm, but we can still try to solve it. So let's start by simplifying the given sat instance. First of all, a simple simplification that you can make is if you identify some duplicate lines, simply remove them. And that can even happen sort of at your text file level. If you're given 1, 2, 1, 2, 17, 1, 2, 17, just remove one line. You don't need to keep duplicate lines. However, it can also be that the line is logically a duplicate, like 1, 2 prime, 17. And there's another line that says 2 prime, 1, 17. Still, you have a duplicate, so you can remove one of the instances of the line, because as you recall, both of these lines mean the same thing, x1 or x2 prime or x17, and then you're saying x2 prime or x1 or x17. So that's a duplicate, you can remove it. Similarly, if you have any duplicate literals in one line, just remove the duplicate literal, x1, x1, x1 or x1 or x4, that essentially means x1 or x4. Now you may want to keep it too, depending on how you're solving it. Maybe you want to keep it because you are somehow dependent upon the three literal in each clause structure. Keep it, but again, if you want to simplify it, you can do it as well. Now, if there is a literal and its complement, simply remove the line, like 1 or 2 or 2 prime. That line is always true. So just go ahead and simply remove it, right? So you can simplify the sat instance. And now let's go into the actual solving it. We can solve it using a simple recursive algorithm. Here's a simple recursive solution. It's a Boolean is satisfiable function. We're given a list of clauses. Just identify a suitable variable x. You can identify the suitable variable x many different ways. If to get things started, you can just say identify any variable x that still is not assigned, and make that to be make that to be true and make that to be false, one by one. So first of all, you set that to be true. Once you set the variable x to be true, of course, the problem structure is going to get simplified, because a lot of clauses which are already true now, those can be removed. Where x is true, that means x prime is now false. So the x prime can now be removed. So you now have a simplified version of the problem. And that's here referred to as the clauses 1. Now you recursively check is satisfiable clauses 1. If you find it, great. You return true with the solution that x is actually equal to true. And similarly, you find solution for the other variables as well. And the other arm of this equation is that maybe x is false. Then go ahead and get the clauses to where you simplify the clauses to be with x is equal to false. And then again, check the recursive solution for that as well. And then if you find true, then you found true. And if you don't find true in either case, then you return that to be false. Okay. So it's a recursive solution. You have just identified some variable x, and you're trying that to be either true or false. And if neither works out, then you say, okay, this formula is not satisfiable. Okay. So let's talk a little bit further on what does that mean to say a suitable variable x. I said you can choose the first variable x to be suitable variable, but maybe you want to think about it a little bit further. Maybe you want to identify the variable x that appears most often. If you do that, if the variable x appears so often that it will actually simplify a lot of clauses. And that will certainly help with the time complexity of this algorithm because the recursive call will be much smaller than the original call. For example, let's suppose your original problem had 1,000 clauses and you identify a variable x, let's call it x1, and you say x1 appears 53 times. And now you're setting x1 to be true. Then all of those 53 clauses are now going to disappear entirely. That means in the recursive call, you're not going to have 1,000 clauses. In fact, you're only going to have 947 clauses. That certainly helps. That means your recursive call is much smaller. We cannot guarantee that, but by identifying a suitable variable x, you can see that it can lead to some significant reduction. And that's what we mean by suitable variable x. Now, you can certainly not think too hard about it and just choose the first variable x, but if you identify a suitable variable x, that can speed up your algorithm. And what's the time complexity of this algorithm? Well, in worst case, it remains exponential. It says all we're saying is t of n is equal to 2tn minus 1 because you have two recursive calls and plus 1 plus some constant time operation. And in worst case, maybe only one clause goes away. And that's why we say t of n is equal to 2tn minus 1 and t of n is equal to 2 power n. In practice, you can do somewhat faster, but remains within exponential time. Again, there you have it, a very simple recursive time formulation for it. So what's the significance of satisfiability problem? It's actually a very landmark problem. It's a landmark result of the Cook's theorem, which is now commonly referred to as the Cook-Levin theorem. And it was the first problem identified as NP-complete by the virtue of Cook's theorem. And the Cook's theorem shows that the SAT is NP-complete because every problem in NP, essentially every problem that can be solved by a non-deterministic Turing machine, can be reduced, can be transformed into an instance of the satisfiability problem. And that result really got us started on this NP-completeness journey and this field of computational complexity that we are all so familiar with now when we study P and the P versus NP problem. But the SAT problem is what really got us started. So in that sense, it's a highly significant problem. It has led to identification of thousands upon thousands of other NP-complete problems, but SAT was the original problem. And it's a very simple problem. Like I mentioned, to convey this problem to somebody, you don't need them to understand very complicated math. You can kind of go to the grade school level and give them a formula and say, okay, go ahead and find it, even without explaining the general concept and the general algorithm. You can give them as a puzzle and they can try to find it, saying, hey, if you find x1 to be true, x2 to be false, x3 to be true, x4 to be true, x5 to be false, the formula works out. And that's quite interesting. So it's a simple problem, it's a natural choice, and it's a very, very, very significant problem here. The Cook-Levin theorem is essentially, and I think the picture of Levin is hiding here, but the Cook and Levin and Turing in middle, this is essentially the essence of the Cook-Levin theorem here, which showed that the problem is NP-complete. That's all I have for you today. We're studying the satisfiability problem. It's a core concept within NP-completeness. So keep learning, have fun, okay?